Hi guys, thanks for joining today's session. Hope all of you can see my screen and you can hear my voice. What are the steps that are in? So we know what is machine learning. I don't want to repeat you, and I don't want to bore you by keep talking about the machine learning again and again. But still, that is a fundamental thing. You should be knowing it. So we know what is machine learning model. We need to the machine learning models, right? So we need to have the historical data. That is the prerequisite. Once you have the historical data in place, you can train the model. Once you train the model, you apply the train model on the test data. Why we are applying the train model in the test data set? Because we wanted to test how well my model is predicting on the test data set. Okay, you can predict the trained data also. Okay, and you wanted to, if you want to predict the test data, yes, end of the day, we are going to predict the test data, right? So we need to predict the test data. And with the trained data, what is the error we are getting it? With the test data, what error are we getting it? Are those errors are seen? That means my model prediction is very good. See, first of all, what is the first step? The first step is you need to train the model. Okay, in the case of linear regression, how do we train the model? We are using this step. Understand the funda very clearly. That is very, forget about all these steps. You need to have the data, all these things, right? This all the things you forget it. And first and foremost, we need to fit the linear regression. This is where we are going to train the model. This is where we are going to train the model. That is what I'm talking. The first step is train the model. Train the model with historical data. Train a model with historical data. So data was given by the customer. So in this case, the data file name was housing data.csv. This is the file given to you. Let's say you joined with the company. Very first day, they gave you this data and they want you to make a prediction. Okay. This data set is not the population data. Again, they gave you some data. So what you do when it comes to supervised machine learning model, you need to split this data in some ratio, okay, randomly. You need to sample this data randomly with some split. Let's say, let's go by 75-25. 75% of the data, you are randomly sampling this data. You call this as a training data. And the remaining 25% of the data, you are using it for testing purpose. Okay. So this data set already they've given you with the input with the output. Look here, this is the data set was given to you. Let me just open. I somewhere opened it. I don't know where it has gone. And still, those of you were able to understand the funda, please bear with us because one or two people still they are not able to understand because they are quite new one. We will see. Try to help them at the very basic level. Okay, so docs.google.com. I just go because my license got expired and some confusion happened. Look here, I just opened this file in the Google Sheet in cloud, and I just opened this file hosting data.csv. This is the data set given to you. They want you to predict the housing price. And okay, no, this one. That is the assignment you all going to work. Okay, and I will give you that one for you all to start work on. Housing data, yeah, this is the one. This is the data set was given to you. Look here. So here they have given you all the input features. This is your labeled output feature. They gave you the input as well as the output. I just simply because I cannot do anything here because some licensing issue and all is there. Though I paid money, these guys they did not install the proper version. Okay, I just copy pasted one second here. Oh, you can't even copy it. So here I can't even upload this file. One second, let me just they are very smart. So here I just copied it. Not copy is not possible. Okay, let me do one thing. If they are that much smart, we are much more smarter than them. Okay, I just open this file using Notepad. Okay, and I just go here and I paste it here. But if you paste it here, I'm not able to. Most features are disabled. Okay, earlier I was able to do it. Okay, now I cannot do it. Let me do one thing. Let me open my Notepad++. But if I use Excel, I can show you the thing here. 1 second, let me just. I try with my AnyDesk. Let me see if luck. AnyDesk to other system. Or else, what we will do is, I will share this file to Gilbert. You connected from your laptop, right? This Zoom.
No, Satya, today I'm traveling.
Oh, you're traveling, right? Okay. I thought if you have an access to laptop, I thought of sharing it with you. And okay, let me do one thing. File open. Okay, let me do one thing. Import. Okay, import my drive. How do we upload the file here in Google docs.google.com? Is it possible to upload it here? So here they have not given any option here. Earlier, I used to upload it with Google Sheets. Let me do one thing. Google Sheets. Yeah, Google Sheets. That is on this in Google Sheets. Now they made everything as commercial. Microsoft earlier, at least this one was available as a free one. See, they are asking all the details. Oh, it's already I did it. It's there. Look here. This is the one already I copied. Okay, size. These are the things were given, right? So including the price. How many columns they've given? 1, 2, 3, 4, 5 columns were there. This is what we used it even in the last sessions to train our model. This is the data set was given to us. The first 4 columns are input fields. This is your labeled output. Okay, the input as well as the output they have given. Okay, this is the data set they've given. Now we need to predict the values for this one, right? The price. Okay, and for this given specification, if the house size is 230 square feet, and if the UDS is this one and the park is this one, MIC is this one, what is the estimated housing price? The actual price was given. This is the one given by my manager. And what is the estimated housing price that I need to pick up from my pick up from my model, predicted by model. This is the model. Sumati, I repeat it for you only, for you and Jivanandam. Predicted here. Okay, predicted value. So what is my model? Gave me some number, right? For example, if I go here, watch carefully. Here we have fitted the model. This is how we need to say, look here, I have given the extrain. What is extrain? Extrain is nothing but all these things up to this input features. Okay. This one is what in the input feature and the price is the output feature. These are all given data set. This is the training data. Okay, so this is my housing data.csv was given. I splitted the data into train and test because I wanted to test once I train my model, how well my model is predicting on the unseen data, which is my test data. So are you able to understand or not? This is very much important. Okay, and train the model with historical data. So here train the model with training data. That is what we are doing it. So look here, that's why I've used the training data. So when you train your model, you need to tell what is the input feature, what is the output feature. We have given the input feature and output feature for the training data set we have given. So and using the model.fit, it will get trained. Okay. First, so forget about the commands. What is the linear regression? What is model.fit? Forget about the commands. Okay. First, understand the big picture. To train a model, you need to have the independent variables and dependent variable. Is it clear or not? Sumati, can you confirm it? We need to use both the independent variables and dependent variable to train our model. Is it okay or not? Up to this, step one is clear, right? So we are able to train the model with the independent variable and dependent variable. Cool. So now my linear regression model is model. You can give whatever name that you wanted. And that's it. We are done with this. The next one is, now we have used the training data, right? So we need to apply this model on the test data. Okay, so look here, this is my model. What is my model name? Model dot predict function. Inside this, we give the x underscore test. What is x underscore test? X underscore test. And what is the difference between train and test? X underscore train and x underscore test. X underscore train is holding the 75% of the independent variables value, and x underscore test holding the 25% of the data of the independent variables. Okay, for example, here I just show you print x underscore test dot shape. So 37 records are there. Okay, and what is the total number of records? HDF, right? Okay, I think HDF dot shape. Yes, in total 148 records are there. The 25% of the 148 records are 37. That is what the X test is holding it. You remember here, we have splitted the given data by 75, 25. 70% of data went into my training data set, and 20% of data went into my test data set. So ideally, if I could have explained it with R programming, right, you would have understood much better, in a much faster way. So here the x underscore train, y underscore, that is the one is confusing you, right? Fine. So you don't worry. Your x underscore test dot ship 37 records 20, which means the 25% of the independent variables data went into my x test variable. Okay. And now what I do is already train my model on the 75% of the training data that I apply on the unseen data x underscore test. Okay. And this is the predicted values for the x underscore test. This is the predicted values. So first we need to train the model and then apply the trained model. Step two is here train the model with the training data. Okay, this is my training data, and apply the trained data, apply the trained model on the unseen data. In this case, the unseen data was test data set. Whatever was there, the 25% of data was there, were there in this test data, was not seen by my model. What is my model? In our case, the model name is model only, right? This model, we have used the training data only. Okay, this does not contain my test data. Remember that. Okay, this model does not have the overlap of these two data. This is very important. One of the interviews they asked, what are the data is there here? Do we have it here? No, the training data is completely different. Test data is completely different. That is what our assumption. This model, linear regression model, we trained with the 75% of the training data set. Remaining 25% of data, what we are doing is we have the remaining 25% of data is available in our test data set. we apply the model which got trained by the training data, which has 70% data in it, on the test data set. Okay, so the test data set, what we have used X test. It doesn't have the dependent variable in it. It has only the input variables, the size, UDS, Spark, MASC. That's all. It doesn't have price in it. Remember very well. So y underscore test is the one holding the price in it. Okay. So here we are applying the model on the X test. Okay, because in this data set we don't have the dependent variable in it. Because my model should predict based on the input variable, my model should predict and give the predicted value. That predicted value we need to compare with Y test. Y test is holding the same 25% of the dependent variable value in it. Are you able to understand or not? See, I will tell you, I'll show you here. So this is my training data. Okay, this is my training data. My test data also will have something like this, right? Same thing, but in the X underscore test, we are having only these 4 variables in it, X underscore test, but the data is different. Okay. Now what we need to do is okay, now let us understand this one. Okay, the big picture. Okay, forget about training and test data set. So what we want to find out here is we wanted to find out the predicted values here. My model will give you the predicted value. How the model will give the predicted value? When you use predict function, it will give you the predicted value. Look here, predict function, predict method or predict function. Model dot predict. This is my linear regression model already trained with training data. Followed by this, I've given the predict method. See here, I just pass the X underscore test, the 25% of the data of my independent variables. I just passed it. This one has all the input features except the dependent variable, and also it has only the 25% of data in it. This data were not seen by my model. So when I apply the model on this unseen data, it gives me the housing price, predicted housing price for these input features. It gave me the predicted the predicted housing price for the unseen data. Got it? Fine. So the next one is, look here. Here, okay, how this predicted value was arrived? Equation. We know very well what is the equation for linear regression. Y is equivalent to, please concentrate here. Let me just, my equation is y is equal to, so here I don't have this one. Beta naught thing is not there. It is there, but still beta 1 into, what is that? Size plus beta 2 B2 into UDS plus B3 into Park plus B4. So here B3. And here it is B4 into MISC. Got it? So this is the one. So Y is nothing but your price, housing price, predicted price. The price will be predicted based on the right side of the equation. So the beta naught is what? That is intercept. What is beta 1 is the slope. Look here. Let us go back to this one. Here it is showing everything very clearly. Look here. So the beta 1 is 3.004. Simply you need to plug in the 3.004. Simply plug in the value for the beta naught. So the beta naught is what? This is the one, 3.0074. And plus, what is the size? The size is nothing but this one, 230.1 into this value, 0.04. Okay. And this is your, please remember, this is your beta 1 and beta 2. Okay. And 0.1797. So the UDS value is 37.8. I think I pressed some key. So the UDS is 37.8 into the beta 2. So the beta 1, beta 2, beta 3, beta 4 are, were computed by my model. We don't have to compute it manually. Got it? So we don't have to compute it manually. So that value was given automatically by my model. So if you add these things, right, you will get the predicted value. So if you plug in the values here, so the beta intercept was already given by my model. Beta 1 was also already given by my model. I think I press some key. Oh, it is fine. For this beta naught and beta 1 and beta 2 and beta 3 and beta 4, right? So beta 3 and beta 4. Okay, recording is going. So the beta naught, beta 1, beta 2, beta 3, beta 4, we don't have to find out. It is already available, computed by my model. That is computed. But in this case, I have used only these two columns, size and UDS. For example, for your sake, I just put this one also here. And here MISC plus Spark. Okay, we got the slope for everything. Intercept 3.049. The beta naught is 3.049. You need to plug in these values. Plus the size is the first occur 230.1 into 0.468 plus the 0.1816 into this value and plus this value into this value plus park, right? So sorry, park into, so park MIS is minus 0.4085 into this one plus the park 0.40663 into this one. You understood that? Simply plug in the value, you will get the predicted value. You see your predicted value is 22, let's say 21.21. And similarly for this predicted value, see the predict function, what it does is it takes each and every coefficient and plug in that values into this equation. Okay, and it gives you the predicted value. Okay, for these three variables, for these four variables, we know the beta coefficients like intercept value and everything. So the intercept values, intercept and slope values, these are the slope values are common for the entire data set. Okay, and if you simply plug in those intercept and the slope values for these values, let us say you are getting 9.8. This is the predicted values for your data set. Okay, and let's say this is your 8.9. That's all. Next one is, now we need to find out the difference between actual and predicted. Actual minus, so this is called your error. Actual minus predicted. The predicted is, sorry, the actual is, this is the one, 22.1 minus 21. 1.1, that is the error. It is called the actual minus predicted is nothing but the error. Okay, simple mass. Let's say you're buying a share. So let's say I predicted the price for Infosys is per share you will get 500 rupees. Let's say that is the predicted value. Infosys, I just predict and say, hey, if you buy one share, so let's say per share you will get 500 rupees profit. Using my model, I predicted it. I have a model. As per my model, per share you will get 500 rupees profit. What you're doing is, okay, you are going by my prediction. You purchase the Infosys stocks, and let's after you purchase, right, you decide to sell it off. That is what your actual price. For what price, how much return you got it per share after you sell it off. That is what your actual. Let's say you got it like 498 per share, you are able to get 498 rupees profit. Now what you are doing is, what is the error? Error, right? So error is actual minus predicted. So 498 minus 500 is minus 2. There is a minus 2. So what you will say, so this guy predicted 500, but actually I was able to sell it off only for 498, but still his prediction accuracy is good. I just lost, the only 2 rupees was the difference. It is not lost, already it is profit, but the only difference is just 2 rupees only. This guy seems to be very reasonable. Henceforth, before I invest money in the stock market, I'll ask him to give the predictions, or I'll be using the machine learning model to make a prediction. But supposing you are selling it at the cost of 200 rupees per share, you are able to get only 200 rupees profit. Instead of 498, you are getting 200 only. What you will say? The difference, they say 250. Okay, per share, you are able to get only 250. So the actual was 250, the predicted was 500. So what is the difference? 250, which means there is a 50 percentage of the accuracy. The accuracy is just 50 percentage only. So in this case, the accuracy is right kind of 98 percentage. My model accuracy. Error. So actual minus predicted is nothing but your error. This is your error. Okay, error, right? So if you sell it off to 250 rupees only, that means right, the 50 percentage accuracy, only 50, the accuracy is just 50 percentage only, right? The model accuracy is just 50%. You say that way, right? If you are able to get, if the value whatever I predicted, if you are able to sell it somewhat close to that, that means the accuracy is good, but still error is there. So lesser the error, better the accuracy. Right? Lesser the error, better the accuracy. You will ask the doctor before surgery, what is the success rate? If I undergo this surgery, what is the success rate? If he says, he will say prediction, right? He will say there is a 98% chance that you will recover. After surgery, if you get recovered completely, right? You will say 100%. Whatever he predicted was correct. So 100% recovery was there. Very good. 100, his prediction was correct 100%, right? So similarly, when you go astrologer, you do the same thing. If somebody tells you, right, at least 90% of whatever thing happened in the past, you will say, this guy is good. Very good, right? The same thing, that's all, you're nothing. Don't get confused. Don't think this is something only genius can learn it. Okay, it's a very simple one. Now you understood, right? So the predicted values are obtained automatically with the predict function or the method in Python by simply plugging in the values obtained, obtained already. Okay, in the training model, when you train the model, it automatically finds out or computes the value, or it estimates the values for beta naught, beta 1, beta 2, beta 3, beta 4. Simply it plug in these values and then it multiply each slope value with the corresponding column value. And then it gives you the predicted value. So this is the predicted value in this case, 21 and 10.4. If you subtract the actual with the predicted, right, so you will get 1.1. This is your error. Okay, here if you subtract it, for example, here 10.4 minus 9 point, it is the predicted, and here this is the one, right? So 0.4, this is the error. This is actually an error. So what we are doing is, for example, in this case, the actual price is 18.5 for this specification. Okay, for this specification, this is 18.5, but my model predicted, let's say 19.2. In this case, what will happen is the actual minus the predicted. In this case, it is a negative value. So end of the day, what we are doing is you are adding all these values, errors. When you add the error, what will happen is the plus and minus will get subtracted. Hence, we will not get to know the actual total error, the effect of the accuracy rate, we do not know. Hence, what we are doing is we are squaring this column, error squared. We are squaring this value. So 1.1 into the same column is 1.21, right? You do this way. So in this case, the negative, what will happen is minus into minus will become plus. 7 into 7 is 49. Now we are going to add all the values. This is called your sum of squared error. You are summing the squared error, that is called your SSE. It is also called as a SSE. Sumati, are you able to get it? Others are able to, the others, they said, okay. But see, it is not that everyone should learn it at the first time. Fine, I'm going to explain it one more time. Okay, but you need to concentrate here. So from the actual, we subtracted the predicted. With that, we are able to get the error. But when we add all the errors, it is not going to give me the correct picture because positive error is there, negative error is there. To overcome that, what I'm going to do is I'm going to square each and every value of my error. Since I'm squaring the error, and when I do the sum of all these things, at the end of the day, you need to sum all the values, sum of all these things. Okay, this is called, since we are summing all the squared error, we call that as a sum of squared error. Okay, and instead of so we can do that this way also. Okay, mean squared error. So what I'm doing is mean squared error. So instead of summing the value, I'm going to take the mean squared error. Okay, here I just use mean here, the average. What is the average error I'm getting it here? Okay. Here also we are squaring the error, but instead of summing it, we are taking the average. Hence, we call as a mean squared error. Instead of summing it, we take the mean on the squared error. This is called your mean squared error. Okay, mean squared error. Sorry. This is called your mean squared error. Since we are taking the mean on the squared error, we are called as a mean squared error. And if you take the square root on this, the mean squared error, we call as a root mean squared error. Because we are taking the square root, the same thing. See, if you take the square root on this value, that is called your root mean squared error. That's all. The lesser the root mean squared error, better the model. Instead of going by the mean squared error or sum of squared error, we use root mean squared error because the root mean squared error will give you the error value in terms of the the unit of measure of your price. Okay, that is what root mean squared error. So now the question is, okay, we have trained the model. We will go back to the big picture, the steps. Okay, first one is you train the model using the training data, and then apply the trained model on the test data set. And finally, what we are doing is we are going to find out the predicted value. So apply the trained model on the test data. Why we are applying it? Apply it in the sense predict the test data price. Okay, housing price. And then what we are doing is we are, this is, you just assume this is my test data set, predicted values. Okay, the 25% data is there in the test data set. So here what I'm doing, I got the root mean squared error for my test data set. Right. So what we are doing is we are using the metrics to measure the model performance. So this is basically give the predicted price. Okay, once you train the model, apply the trained model on the unseen data to get the predicted price. And now what you're doing is you are comparing the predicted price with the actual price, actual versus the predicted price. And then what you do, that is where you do root mean squared error, everything. You remember, this is what we have done it here, root mean squared error. So here we have compared the actual with the predicted. That is what your error. Instead of literally going by the error, we are squaring the error. And then we are taking, or instead of squaring it, we are taking the mean squared error, and then we are taking the square root of mean squared error. So, right, so we are using the matrix now. So evaluate the model using root mean squared error. Okay, this is the metric. So now the question is, somebody asked, what is metrics? What is metric? It's something like, we use some standard values. Okay, we use some standard values, but when it comes to RMSE, there is no standard value. So in this case, what we are doing is we are creating more than one model. So model one is having all the 4 independent variables, and we are going to create another model. Model 2 is holding only the 2 independent variables. Why 2 independent variables? Of the 4 independent variables, 2 independent variables were not at all helpful, or it doesn't have the predicting power. Hence, we dropped the, with this 4 independent variables, what is my model? Root mean squared error. And with, for, after removing the 2 columns, which are not at all helpful, right? So we are checking the root mean squared error for the model 2. So of these 2 model, whichever model has lesser error, that means that model is the better model. So let's say model 2 or root mean squared error is something like 1.2, whereas this one is 1.8. So which one is smaller? This is a smaller one. Hence, the error is less. The accuracy is obviously good. Look here, in this case, per share 500 rupees, you will get profit. This is the predicted one, but actually you got 498. Error is less. That means the accuracy is good. Whereas in this case, the error is high, right? So 500 minus 250. So that means, since the error is more, the prediction accuracy has gone down. Got it? This is the big picture. Forget about Python, all the things. Okay. First, understand what we need to do. First, we need to train the model, and then we apply the trained model on the test data set. And then what we are doing is, why we are applying the model in the test data set? Because my model never seen the data that were present in the test data set, right? So with the unseen data, whether my model is predicting well or not, right? So for that, to test that, we are applying this model here. And then, okay, I applied the model, my model predicted the data. Now we are comparing the predicted with the actual value. If the predicted and actual values are somewhat close by, then we say the model is, model accuracy is good. But what we are doing is to check. We have a shortcut. We have something called metrics or MSC. For example, in the case of healthcare, let's say you go for a medical test. Okay, let's say you have a fever. When you go and meet the doctor, they'll check the heart rate. Even they check for your BP, also blood pressure, and temperature. They check it. The HR, BP, temperature. These are all like your metrics. These metrics can help you to find out how well you are doing it. Your heart rate is less than 100, then you are good. Okay, and your BP is let's say 120, 80, or within that thing, right? Then you are good. Your temperature is let's say it's a 98.5. So this is good, right? There are some standard values are there. With this metrics, the HR, heart rate, and BP, temperature. So you doctors, they use the term vitals. If somebody, your relatives are very sick, and if they get admitted in the ICU, when you ask the doctor, say all her vitals are normal, which means the heart rate, BP, temperature, everything is sugar, everything is good, including her kidney function, everything is. Only thing is in for some other problem. Okay, so metrics using this kind, in this case it is metrics. Okay, HRB, but don't try to convert this in your local language. So with this example, you try to understand what is metrics. So in the case of healthcare, they use the heart rate. They use the heart rate and BP. What is her heart rate? Heart rate is less than 100. Okay, good. BP is okay. Temperature is let's 99 something. Is there okay, but still little bit high. Okay, fine. But vitals are good. With this only they are going to determine. Similarly, with this they are going to determine whether you are healthy or not. Okay. Similarly, we use metrics in the case of machine learning model to measure, are we really doing good job or not. Even in the case of project manager, I don't know. So if you become a project manager, you will get to know that in the project management, they will set something like metrics. They measure some metrics, schedule slippage. Schedule slippage. For example, the project duration is only 8 months. Have we completed the project, on or before 8 months? If you have not completed on or before 8 months, then you have slipped the schedule. So in this case, the matrix is schedule slippage and defect leakage. You have something of defect leakage. How many defects we got it? So if the defect is well within the limit, then it is good. So the defect is not much, and there are no schedule slippage. We are on time. So these are the metrics. Similarly, RMAC is one of the metrics. Some cases they use mean squared error. Okay, instead of taking if you square this value, you will get mean squared error. You understood? To measure something, you need a matrix. Okay, that is what metrics. So to measure the model, how well it performs, we use something, MSC, the root mean squared error. Now, if I go back here to my model, Okay, we train the model. Look here, you directly go here and you take a look. Simply, all you need to just simply execute each and everything. I'll just share the code right after the session. Simply execute each and everything, but make sure that you are keeping the housing data.csv in this folder. Create one folder in D drive and put it here. You need to specify the correct path and the correct file name. That's all. If you execute this one, it will work. And just fit the model. This is where we are training the model, right? So this one. And before we train the model, what we are doing, all the steps I explained. Okay. And the next step is we need to check. We need to do the we need to check the root mean squared error. Look here, mean squared error. I took the square root on the mean squared error. Okay. So here I have used the dependent variable of my test data set and predicted value of my test data set. I just pass this in the actual and predicted. You need to pass the actual and predicted to this function. It gives you the root mean squared error, but it gives you the mean squared error. If you take a square root, you will get mean squared error. Okay, now the question is the root mean squared is 2.047. Can I say my model is doing good job? 2.04 only, it's a very small number. Can I go ahead with this? So you cannot simply say this is a lesser error. If you take any machine learning model, the ultimate goal is reduce the error. If you reduce the error, automatically your accuracy will go high. Okay, now what can I do? So now what I do is in this model, I have used all the 4 independent variables. Okay, and then with this correlation matrix, the correlation matrix is not there. With this correlation matrix, I was able to understand these 2 variables are not at all having any predictive power because these 2 variables are not correlated with my housing price. Hence, drop this and you create another model. That model should have only 2 columns in it. Look here. Here I did the same thing. Look, in this case, I have used size and UDS. I removed the park and MIC column. So here I just define my independent. X is holding size and UDS independent variable, and Y is holding the price. Look here. When I just splitted this data into train and test data set. And the next one is I'm just fitting the model. I have given the different name here. Init fit 2 and model 2. And model 2 dot score. I need to use it here. Okay. For example, if I do this, 0.9044 and model 2 score, yeah, it's already there. And model 1 score was there earlier. And next one is I'm going to apply this trained model 2 on the unseen test data set. Model 2 dot predict X test. And then what I do is I just compare, what is my model's accuracy here, right? So here I just use the R squared value. Okay. Or you can use something like mean squared error also. I will show you a little later. Okay. So in this case, we are using R squared. Instead of using the root mean squared error, we are using the R squared. Here we can see the training data set R squared is this one. Test data set R squared is this one. More or less, it is overlapping. What is R squared? We discussed yesterday, right? R squared. What is R squared value? The proportion of variation explained by my independent variables. Okay, how well my independent variables are helpful in terms of predicting my outcome variable. So in this case, you just think, right, 90% for the training data set, whatever the independent variable that I used it was helpful in terms of explaining the variation on my dependent variable. This is the thing. Okay, you need to see this. See, you are getting these values. End of the day, everything is given automatically. See the actual minus predicted. You don't have to do it here. 1 second here. Yeah, instead of using the mean squared error, okay, we can use mean squared error. Look here, I have used the mean squared error. We have something called metrics package that is available. Okay, in that library. Okay, we have something called mean squared error method. You need to pass the actual and predicted value. When you pass the actual and predicted value, so this is the one, the actual and predicted value. Simply you need to tell this to this function, and this function gives you the mean squared error. What is the mean squared error? So this is the one, the mean squared error. Okay, it gives you the mean squared error, and then when you take the square root on the mean, you will get this one. So for model 1, this is the one. For example, if you're a model 2, if you get 2.00, still the value is very less, right? The 2.00 is less. So in this case, I'll just show you what is the difference here. I just simply copy paste this one. Yeah, here already this is for that one. Model, okay, and here the model dot predict, we got that value predict, and here mean squared error is this one. Predict is the one holding the model, that one's predicted value in it, and this is the one we are getting it. Let me do one thing. In this case, model 2, and so in this case, I'll just use this one. Model 2 dot predict, this one, let's say predict 2. I just call this a predict 2. Two point zero three, and that is the root mean square error. Here 2.04 we are getting it. For model, this is my model name. Here I have used 4 independent variables. All the independent variables, independent variables. For this, what is the root mean square error? 2.04 something. And model 2, here I used only the 2 independent variables. 2 independent variables. For this, the root mean squared error is 2.03. Of these two, which one has less error? Obviously, this one has less error. Hence, model 2 is predicting with the higher accuracy compared to model 1. So are you able to understand? How many of you are able to understand? How many of you are not able to? How many of you still not able to understand? Is it clear? Okay, tell me, those, okay, Karthik and Sumiti, now you are able to understand, right? Very good. So that's all, you are nothing. See, if you are having a rigor to follow this session, right? After 6 weeks, who knows? You might be a rich person, right? That's all. See, there are, once again, there are, continue the train. So model and model 2, what is the RMSE for this? 2.04. What is the model 2 RMSE? 2.03. So since this model has lesser error, it has a better accuracy. So how do you decide, what made it to get the lesser RMSE? The simple reason is these two independent variables are highly correlated with my dependent variable. But in this case, of the 4, only 2 of them were highly correlated with my dependent variable. Remaining 2 independent variables were not at all correlated with my dependent variable. Since those 2 independent variables were not correlated, though those 2 independent variables were not correlated with dependent variable, I include in the model. Since I included those 2 variables which were not significant, it increased the error. Got it? So this is there are a number of reasons for getting the lesser RMSE or getting more RMSE. This is one of the reasons in this case. The simple and straightforward reason is this one. Got it? So how did you do the feature selection? In the interview, they'll ask you, how did you do the feature selection? In the case of linear regression, we have completely relied on the correlation matrix. Correlation matrix that helped us. And we have different other techniques, recursive feature elimination, stepwise regression. Likewise, different techniques are available using which also we can do the feature selection. But the correlation matrix, in our case, it was very much helpful because we were not using uh, hundreds of independent variables. Oddly, we are using 15 to 16 independent variables. And of the 15 independent, or let's you just tell them 12 independent variables, we are using it, 12 independent variables. Of the 12 independent variables, hardly 8 independent variables were highly correlated or correlated with my dependent variable. Remaining 4 variables were not at all correlating, since it made it was a very simple thing for us to decide to knock out the remaining 4 independent variables and keep only the 8 independent variables in our model. With this independent variable, my model was predicting well. But these independent variables were not correlated among themselves. You need to tell that point. There should not be any correlation between the independent variable. So there should not be any correlation between these independent variables. So Park and MIC should not have the correlation, and size and EDS should not have correlation. Okay, and UDS and size should not have correlation. These are the independent variables. Size and price can have. This one should have the correlation, and UDS and price should have the correlation. Park and MI should have the correlation price. It should not be like MIC and Park should have correlation. No, it should not be. It is against the rule. Okay, it is violating the assumptions, linear regression assumption. If there is a correlation between the independent variable, that is, this is violating the linear regression assumption. Got it? I explained you in depth. With the Excel, I think you would have understood, right? So what is error and what is error, sum of squared error, what is mean squared error? So these things should come to your mind the moment when somebody says what is SSC, sum of squared error, sum of squared error and root mean squared error. If somebody tells, right, you should visualize this in your mind in a matter of jiffy. You can tell, oh, this is the what he's asking. So square all the error and take the mean of all the error and take the square root of that is what root mean square. So lesser the error, better the model. Very simple. So how do I compare that? Is there any benchmark? Create 2 different models. Each model have different independent variables, and blindly we don't keep 2 different independent variables, but we just use the correlation matrix as the basis. With the help of correlation matrix, we understood of the 4 independent variables, 2 independent variables were completely useless. Hence, we removed that from the model and we fitted the model. After we kept only the independent variables that were statistically significant. In other words, those 2 independent variables have higher predictive power. We had it in our model, right? So the model error got reduced. So of these 2 model 2 is really doing good job because the error is less. Okay, the next situation is, okay, you have used the training and test set. For this, you have the whatever the training and test set you have used it, same training test set you have used it here. Right, hence you are getting this one, fine. But if I give you the different training and test set, let's take for example model. If I give the different training and test set, will this remain as it is? That is what I discussed yesterday. So we have something called bias and variance. Okay, when you use a different training and test data set, right, your variance should be less. Even though your bias is a little bit higher on the side, variance should be less. If the variance is high and the bias is also high, then your model is not generalized well. Bias na error. Okay, bias is something like error. You just think that way. And bias and variance. Variance is the error variance. Okay, error variance. Okay, if the variance is too much, let's say we have 5-fold, and each fold, when I run my model, right, it's something like an athletics. I just give it an athletics. So if an athletic runs very well, let's let's say 5 kilometers. if an athlete, or let's say 1 kilometer, right? Then if an athlete runs this 1 kilometer in 2 minutes in your school, that is good. But the same athlete, if you ask him to run uh, in this one, what is that here? In the real sport, right? Ground. So if he takes the 1 kilometer, less than 2 minutes, it is good, right? So somewhere it is good. So if you ask him to run in different ground for 1 kilometer, and if he takes only 2 minutes or somewhat closer to 2 minutes, then there is no variance. But when you ask him to run your school playground, it takes just 2 minutes to cross 1 kilometer. Whereas if you ask him to run in the, in this somewhere in the sports ground, right? If he takes 5 minutes, then there is a variation there, too much of variation. Okay. And here, if it takes, let's say 1 minute, 45 seconds, right? Then it is good. And all the other ground, let's 2.2 minutes and 2.5 minutes and 2 minutes. And here, in the real thing, right? Production, once you deploy your model, the production, if it is, let's say the error is much lesser than compared to your other thing, right? Then it is good. But end of the day, it should not be like this. Let's, in this ground, you took 3 minutes. In this ground, you took 5 minutes. But here you took just 2 minutes. And here you took 5 minutes, 4 minutes. That means 3, 5, 4 minutes with a different training data set. The error is very high. And also the variation is also very, somewhere it is 5, 3, and 2. Too much of variation is there. It should not be like that. Okay. Anyhow, we will discuss the bias variance in the next session. So to address the bias variance or to deal with the bias variance is a trade-off. We use one of the techniques called cross-validation. I discussed about the k-fold cross-validation in yesterday's session. You just watch my video one more time. Okay, fine. And the next one is validating linear regression model assumption. We will take a look at this one now. So what is, 1 second, let me just stop this.